Hey guys, welcome to lecture 15.5. This will be the last lecture from this series, from lectures 15. In other words, we'll be finishing with integral calculus for functions of a single variable. And in today's lecture, I'd like to discuss about series of functions, power series, and of course, how they're related to integrals. Well, so far we have seen how we passed the limit inside an integral. We have seen a bunch of theorems, like the dominated convergence theorem or uniform convergence theorem or bounded convergence theorem and so on. But now in this lecture, we will see how to swap the integral with the series of functions or power series. And I will say a few words about for this to happen, we need what we will call the uniform convergence of the series of functions. Apart from that, we will also be talking about the special case of a series of functions, which will be the power series. And we will see a bunch of, basically I will go do a recap of some notions which were learned, I believe, in calculus 2. About some special, some power series for some elementary functions. All right, so let's dive in directly. Let me start with some basics. Like I said, I want to do a little bit of basics about series of functions. So let me start with the definition. First, let me recall some things. Let's say definition of one. Some basic things about series of functions. And let's consider a sequence of functions, right, Fn. And I will define this on a closed and bounded interval AB, and this would be a real valued function. So this be a sequence of functions So we say that the series, let's just say the series of functions, I want to make myself very clear with this, and we'll denote this in this way. Right, as you can see here, I have an Fn, but I also put here Fn of x because I want you to distinguish between the two. I want you to distinguish between a series of real numbers and a series of functions. So that's why I will put the argument there, Fn of x. Right, so we say that the series of functions, converges pointwise right? If its partial sum if its partial sum let me denote this in Sn of x, right? Which will be the sum from k equals 1 to n of fk of x. Just like in the case of a series of real numbers. So if its partial sum converges pointwise on the interval AB. Well, if Sn of x converges to f of x, right? If this converges, then we say that then the sum of Fn of x is nothing else than just the function f of x, right? So that's basically the definition. It boils down to the convergence, the pointwise converges to its partial sum, just like in the case of series of real numbers. All right. Now let me point out something. If the series, and I'm going to take this in absolute value, is convergent, maybe, then we say that that the series is absolutely convergent. Well, basically, this was pretty easy to see. So, and probably this, as you can imagine, the same thing will happen for uniform convergence. So, definition 2, it's basically the same. Let me just write it just for the sake of completeness. So we have a Fn, a sequence of functions. And in the same fashion, we say that the series of functions and let me just denote this. Well, this series of functions this time converges uniformly if, guess what? If its partial sum converges uniformly, right? So converges uniformly on AB, right? If its partial sum again, let's denote it as Sn of x converges uniformly, right? So it's basically the same thing. It's the same definition. The only thing we replace the pointwise with uniformly. Well, if Sn of x converges uniformly to the function to a function f of x, right? But then we say that the sum of the series is actually the function f of x for all x in AB. All right, so these are the two definitions. Well, they're pretty natural if you think of it. You can basically we just translate the definition, the usual definitions from the series of real numbers, but now we learn a little bit more. We learn about that the sequences of functions can converge uniformly, not just pointwise. All right. Well, in the case of series of and sequences of real numbers, even we have Cauchy criterion for uniform convergence, and let's state that it's a very important theorem. The theorem 1, Cauchy's criterion for uniform convergence. And basically, it says if I have a function, a sequence of functions, right? We will have a necessary and sufficient condition for uniform convergence. So then the series of functions Fn converges uniformly let me write it here. So converges uniformly right on AB if and only if. So I'll put here if double F. We have the following: for any epsilon positive, there exists a rank and epsilon positive integers rank such that for all n greater than this rank and epsilon, and for all p a positive integer, and for all x in AB, we have that the absolute value of these terms after n, fn plus 1 of x plus fn plus 2 of x plus so on, fn plus p of x, they don't matter. So the sum is less than epsilon. So that's a very important criterion. You can actually use this definition to prove uniform convergence, but it's a little bit more, you have to be careful. It's a little bit more pretentious when you're trying to prove this. But there is another theorem which I think this is the most useful theorem when you prove the uniform convergence of a series of functions. And this is what we call the so-called Weierstrass M test. So theorem 2. And this theorem, you learn it actually, I think even in calculus 2, if I'm not mistaken, but definitely you'll learn this theorem in an advanced calculus course or every basic analysis course for sure. Maybe even in an introduction to analysis course. I believe that happens as well. If not, calculus 2. Anyway, so this is what we call the Weierstrass M test. And in this case, we will relate there will be a relationship between the series of functions and the series of real numbers. You will see that one of them will dominate the other. So it's in a certain sense, it's somewhat called like dominated convergence. But anyway, so now let us consider Fn again be a sequence of functions. We have a sequence of functions. So if there is a convergence series of real numbers, right? Let's name it. So this is the sum of an. So this is a series of real numbers, so there is no x there, such that the sequence an will dominate the such that we have this condition. Let me write it like this: fn of x in absolute value is less or equal than an, right? For all n, for all x in AB. Then guess what? Then the series of functions, it's very important to specify that, Fn of x is uniformly convergent. In fact, let me write it like this. All right, that's a very useful theorem. It's basically, it's very helpful if you have if you're trying to prove the uniform convergence of a series of functions, then you can just take the sequence Fn of x, then you try to find a series that will dominate this sequence in absolute value, and if that series of real numbers is convergent, then there you go. You just get uniform convergence. It's pretty easy to get uniform convergence by using this. But there are some cases where, and we will see in applications when that's the Weierstrass test doesn't always work. So there are some cases when we have some kind of alternating series, just like when I say alternating series of functions, just like in the case of series of real numbers, when you cannot apply, when Weierstrass m-test is not conclusive. So therefore, we cannot use it. So we're trying to use other theorems, and there is the so-called, well, there are actually two theorems, but I'll blend them into just one theorem. It's called Abel-Dirichlet criterion. It's a version of the same criterion from series of real numbers. And you will see how this will be useful when we'll see examples which the Weierstrass m-test will fail, and then we'll make use of the Abel-Dirichlet criterion. You will see, so bear with me. We'll see in applications of these theorems in moments that will follow. All right, so first let me tell you the statement of this theorem. So again, let me consider a sequence of functions. And such that I'll have this condition such that there exists, let's say, a positive real m, constant m, such with okay, with the risk of repeating myself, I think it sounds better, such that for all n greater or equal than 1, right? And for all x in a, b, we have that this condition, so the partial sum is bounded by this constant, right? So we have this sequence of functions which has this property. All right, great. And now let me consider another sequence of functions. So let Gn be another sequence of functions and now this guy that converges pointwise. Okay, let me be like this. Converges monotonically pointwise. And uniformly and uniformly to 0. So converges monotonically pointwise and uniformly to 0. Then guess what? Then the series of their product, series of functions, and this is the series Fn times Gn. Guess what? Is uniformly convergent. So it's a very useful criterion. Usually we apply this, just like I said, when Weierstrass M test fails. And of course, there are plenty of other versions of this. There is a theorem of Abel, there is another theorem of Dirichlet, but I combined the two and I just made it one theorem because we're going to apply it in this way. All right, as a particular case, let's just say corollary to theorem 3, say corollary 4, it's called Leibniz criterion. Again, let's consider a Fn be a sequence of functions. Right? And this sequence of functions such that has this property Fn converges uniformly to 0. Let me write it like this. Right? And then the series this alternating series of functions converges uniformly to 0 as well. To 0. So, of course, this is just an application of Abel-Dirichlet theorem. So it follows immediately. You just take Gn to be negative to the power n, constant, so alternating constant, -1 to the power n, and that's it. But now, oh well, there are plenty of other things to discuss, but like I said, I don't want to do a course in basic real analysis, and I'm just covering what I consider to be the most useful, most basic and useful facts that will solve, that will allow us to solve problems. Well, now, just like like in the previous lectures, let's see how we can transfer integrability when we deal with series of functions. And we have this theorem, theorem 5, let's say. Write it in this way, transfer of integrability. So I'm curious under what conditions I can swap the series of functions with integrals and so on. Well, again, let's consider a sequence of functions. Right? and we assume that Fn is Riemann integrable. Okay. All right. If let's write it in this way, if the series converges uniformly to a function, let's say f of x, where f is defined, then f is also Riemann integrable, and not just that, on interval AB, and moreover we have this, and let me write it in this way, we can commute the infinite sum with the integral. We have the series and this would be the integral. So the series of the integral will be the integral of the series. Well, I should have put it the other way around. Anyway, it doesn't matter. And moreover, this is nothing else than just the integral from a to b of f of x dx. So we have this relation. So like I said, we need uniform convergence. So we need to make sure that our series is uniformly convergent. If this is uniformly convergent, we're safe to swap the series, the infinite sum, with the integral. Well, and let me point out them. Well, I only talked about transfer of integrability because I like to talk about only about integrals. I'd like to emphasize more on that as we're talking about the integrals. But let me just say that the same thing will happen with continuity, with differentiability is in the same way. So I can integrate term by term, and like in this case, I can differentiate term by term as well, right? The infinite series. All right, so this is a very useful thing. Like I said, I think this is basically what I would like to just say about a series of functions. And now let me talk about a special case, and which is given by, so this was series of functions. All right, I should have said here, let me put it like this. This is the first thing, series of functions. And now the second thing is special case, which is given by power series. All right. Okay. So, well, this is nothing else than just a special case. So this is a special case of series of functions, which is given by, it's a special case of the following form: a0 plus a1x plus a2x squared plus anx to the n plus so on. Right? What do I mean by a special case? Well, I mean that fn of x is nothing else than just a n x to the power n. So that's my series. You want, or if from 0, that's what we call a power series. Right? Okay. And we're wondering the same thing. If we have convergence, what type of convergence? When do we have pointwise convergence? When do we have uniform convergence? Well, maybe there is something that is special in this special case about the convergence of this type of series, of this type of powered series. Well, but first, before we even go and talk about that, let's see some examples, some easy examples. So we're wondering examples. So, for example, we can have power series which are convergent at the origin. So what kind of choice should we take here? Sorry. Let's say only at the origin. Let me be specific. So if we want that, we can go with this. N factorial times x to the n. So this will be convergent only at the origin. Or if we want to take a power series, give an example of a power series which is convergent for any for any real x. Well, we can take this example, 1 over n factorial times x to the n, right? And what kind of the third scenario, we can have a convergent, so we can have power series which are convergent up to some real number, and then they diverge from that real. For example, we have convergent for any real x which is less in absolute value than a positive number, and then will diverge for any real x which is greater in absolute value than some constant, some positive constant. And that positive constant is what we will call the radius of convergence. All right, so let's write this. So power series for which there exists positive r such that the series converges at any x with x in absolute value less than r, and the series diverges for any x with x in absolute value greater than r. Well, this number will actually define it, and we, by the definition, this is nothing else than just the supremum of this set, the supremum of all x in absolute value for which the power series converges. So that's the definition. So that's what we call the radius of convergence. Again, I think you'll learn this in calculus 2 as well. So I'm just basically reminding you. And well, there is a way to actually compute this. And there exists a theorem which will allow you to compute the radius of convergence. And let me just state it briefly. And that's pretty much, again, was given in calculus 2. So if we consider the power series, let's say, right? And if we take this rho, define rho in the following way. So this will be the limb sup as it approaches infinity of the end root of absolute value of a. So we're going to take this. So this guy, then the radius of convergence right? The radius of convergence will be given by is r equals 1 over rho. But this is how we compute the radius of convergence. Of course, you can apply the ratio criterion, or instead of computing the limb sup of the n root of an of absolute value of n, you can compute the limb sup of the absolute value of an plus 1 over n. So basically, it's the same thing. Either way. And now we would like to see under what conditions we can integrate term by term. Well, just like in the case of series of functions, well, the same thing happens. Integration term by term. Right? We say that if the power series right, has the radius of convergence r, which is positive, and if the sum of the power series is f of x on the interval for which x is less than r in absolute value, then we have the following. So we can integrate term by term. Don't have any problems with that. And well, as you can imagine, we have the following equality. So we have no problems in integrating term by term. It's just like in the case of more general series of functions. So, but now, all right, we can integrate term by term, but there's an important question that we could ask here. So under what conditions we can write a function as a power series? So we can, let's say we can, at the origin, for example. So under what conditions can we express f of x as this power series? Right? For example, this coefficient an, right? So this guy here, this is nothing else than the nth derivative at the origin over n factorial. So under what conditions? Well, you'll be tempted to say, maybe if I have the function to be infinitely differentiable, maybe I could do it. But that's not enough. So C infinity is not enough. And why is that? Well, we have this counterexample, and you can work through it. I don't want to go into it. The counterexample is the following. So let me write it. It's a very famous one. I usually put this in a homework and you can find it in any advanced calculus textbook. So it's e to the negative 1 over x squared for x different than 0 and 0 is 0. So this definitely can prove that this is C infinity, the entire real line, but all derivatives you can prove by induction at 0 are 0. Well, by induction, but first you have to take the first derivative, you have to do a substitution. Anyway, it's a bit tricky, but you use L'Hopital rule, and then when you write the end derivative, you use the induction hypothesis, and then you write this in terms of a polynomial and so on. Anyway, I'm not going to go into details, so I'll leave it to you as an exercise if you want to have fun with it. But that's a pretty nice exercise for you to do. All right, and now, because I don't want to dwell too much on theory, let me just mention some examples of power series. So we'd like to see what kind of some examples of functions, of elementary functions, which can be expressed in this way that you see here, like this, right? All right, so let's see some examples. All right. So the first example that I have in mind is a very important one, the binomial series. Which basically is like this. So 1 plus x to the power alpha is nothing else than the sum, the infinite sum from n equals 0 to infinity of alpha times alpha minus 1 times alpha minus n plus 1 over n factorial times x to the power n, right? So this is the power series expansion at the origin. Well, for alpha, x is less than 1, let's say an absolute value. All right, and now let's see if we take some particular cases. For example, let's just take, we take x to alpha to be negative 1. What do we have? So we have 1 over 1 plus x this is right. And of course, if we take alpha to be 1, we have the classical yeah. If we take x to the negative x, so basically we can also have the classical geometric series, right? These are the geometric, in fact, let me write them here. All right, let's see the third example. What else can we do? Let's say if we take alpha to be 1/2, for example, right? What do we obtain? So we take into binomial series alpha to be 1/2. So there we will have that the square root of 1 plus x will be nothing else than just this series. This will be nice. Okay, from 1 times, and here I'll have the double factorial, and I'll explain immediately the notation. And this will be 2 to the n times n factorial times x to the n. Well, this guy here is nothing other than just 1 times 3 times 5 times so on times 2n minus 1. All right, let's see, what else can we do? Of course, we can take x in through x squared, and we're going to get that 1 over 1 plus x squared is this series. So why am I doing this? Because I like to integrate this at some point. And for example, if we integrate this, or we obtain the following. So integration. So integrating 4. What do we get? So we get the following. So we get the series, the power series for the arctangent function. So this would be all right. And again, we can play around. We can take now x to x squared, and we can obtain the logarithm. Again, x to x squared. And we obtain the following interesting series for log of x plus the square root of 1 plus x squared. This is, here I'll have the 2n minus 1 2n. Right? What else do we have? If I take x to which one? Yes, if I take number 3, right? So in 3, if I take x to negative x squared, so take x to negative x squared and integrate. So if we do this, we're going to get the following very interesting series for the arc sine, and we'll see this, we'll derive this in a very different fashion at some point when we'll talk about differential equations. In fact, I have a big surprise for you at the end of the course, which will be Euler's evaluation of the series 1 over n squared, and we will use differential equations to solve that. But that will be at the very, almost at the very end. It's actually, there will be a devoted recitation for this. So we'll have that this is 2n minus 1 double factorial over 2n double factorial times x to the power 2n plus 1. Yeah. That's a very important series. Like I said, we can actually use differential equations to do this, but either way. All right, so and also let me just mention the classical. I don't want to forget about these, about e to the x and logarithm, because we will use this. So e to the x as this power series. And the logarithm log of 1 plus x. This would be all right. So these are the power series for elementary functions. So you can express them in this way. In fact, you can play with them. I just explained a bit how to derive each one of them. So as you have seen, most of them can be derived by just using the binomial series. All right. Before I even go, let me just give you a quick example on how to use, in fact, let's do a little more now on applications. And well, the first application is the Euler's. Let me write it here. A quick application, the convergence. We'll see what kind of convergence of Euler's dilogarithm. And when Euler's dilogarithm is given by this Li of 2 of x is given by this series x to the n over n squared. We would like to see things here. Well, I don't want to say anything about x at this point. So we'd like to see the domain of convergence. And another thing that I like to answer if LE is, this is more like a question, is this function, the Euler's dilogarithm, uniformly convergent? On the domain of convergence. On its domain. So, but first we have to determine the domain of convergence. Well, let's just say this is x is less or equal than 1. All right. So the domain of convergence, well, as you can see, so at x equals 1, what do we have? We have that this is nothing else than just this series, which is convergent, right? We'll prove this, that this is, the sum is pi squared over 6. So, and at x equals -1, we'll have that, oh, sorry, yes, this is one here. Is this series, which is again converged by Leibniz criteria. Great, so I eliminated the endpoints. So let's see what happens between them. So for x in absolute value less than 1, then clearly you can fn of x, or let's just say the absolute value of fn of x, which is the absolute value of x to the n over n squared, is less than 1 over n squared. Let's denote this by an. And also, the series of an converges. So I don't have any problems. So well, is uniformly convergent. But I forgot to say the domain. On the domain, on the entire domain, let's say. And I forgot to say, because I only checked the endpoints, but it's the interval -1, 1. But now, okay, let me just go back because I jumped from one thing to another. I only verified at the endpoints, but you know, we can also say that the limit as n approaches infinity of x to the power n plus x to the power n plus 1 over n plus 1 squared over x to the n over n squared. This limit will be the absolute value of x. So between if this is less than 1, then you have uniform convergence. So the domain will be -1, 1 open, and then you need to check them at the endpoints. And as we have seen, at -1 is convergent, at 1 is convergent. So the entire domain of convergence is the interval, the closed interval -1, 1. All right, I hope it makes sense. I did not explain in the best way, but I think it's pretty clear. All right. Now let me give you another example, another application of Weierstrass M-test, but this time this problem has nothing to do with series of functions. So let's see, application 2. Basically, we want to find the limit as n approaches infinity of 1 to the power n plus 2 to the power n plus n to the power n, everything over n to the n. So that is the question. In fact, let me just tell you in fact, we will show that. Just tell you the result. This is a very famous problem. That this limit, how should I call this? Let's just denote this by xn. We show that the limit as n approaches infinity of xn is e over e minus 1. It's a very nice problem. As you can see, I cannot apply the Cezar lemma because depends on n, so there is nothing I can do. So nothing goes away, unfortunately. So I should do something else. Well, this is equivalent with showing that the limit of the following: 1 over n to the power n plus 2 over n to the power n plus plus, let me leave the last one, which is 1. So e over e minus 1 minus 1, e minus 1. So this will be 1 over e minus 1. So I want to show that. So if I show this, then I'm good. And what I'm going to do is the following. So I'm going to consider, so I'm going to fixate k, and I'm going to consider a sequence of functions, but that sequence will be defined on the positive integers. So let us consider u of k, let's say, and this would be with the values in the non-negative reals, and this will be given by the following. I'm going to define it this way. I want to emphasize that. So uk of n will be the following. It's 1 minus k over n to the power n for k from 1 to all the way to up to n minus 1, and 0 for k greater or equal than n. Well, it's pretty clear that xn is nothing else than just the sum of uk of n. Is the series of this, right? Great. And now for k fixed, so arbitrary and fixed. So we have that the limit as n approaches infinity of uk of n, so this time I'm taking the limit as n approaches infinity, will be what? Will be, it's e to the negative k, right? Great. But also, so on the other hand, so we want an inequality for something that will dominate. All right, so since log of 1 minus k over n is less or equal than negative k over n, right? For all k 1 to all the way to up to n minus 1. Right here, this is obvious because we use the inequality that log of 1 plus x is less or equal than x, right? And thus, we have that uk of n is non-negative, but it's also less than e to the negative n. All right. Right, for all k n. But also the series of this is convergent. That's beautiful, because now we know, so by the Weierstrass-M test, right? By the Weierstrass-M test, this series of functions is uniformly convergent. That's great, because now we can pass to the limit. So finally, we can have that the limit as n approaches infinity, right, of xn is the limit as n approaches infinity of the series of uk of n. And we can swap the limit, we can put it inside, so this will be the series this guy will be nothing else, and so the limit, this will be e to the k, e to the negative k, sorry, and this is just a geometric series. You can sum it up and it will give us 1 over e minus 1, and that's it. You see the main ingredient here was, well, of course, we need to define this sequence of functions. And then we just need to virtualize M test. So that was the ingenious part, let's say, for this problem. It's a very nice problem. It's pretty famous at this point. Time is running by, but I have plenty of other applications as well. So since we're talking about limits of sequences, let me give you another one. And here we'll use, well, I want to use also Abel-Dirichlet theorem. But first, this is some all Putnam problem. So basically, find the limit as n approaches infinity of the product 1 plus k over n, the power over k. I hope this is right. All right, if you look at it, and we have seen in previous lectures that this kind of rings a bell in the sense of, well, maybe we can use the Riemann sums, right? And yes, we can do that. If we take the log of this, we have a product, we can take the log, we can consider this the sequence of the natural log of this. So it will turn the product into a sum. So by using Riemann sums, this will converge to an integral. But we should be careful with that integral because that would be an improper integral. So let's do that. So let's consider, so let AN be this sequence. All right, and we consider the sequence Bn, and this Bn will be nothing else than just a natural log of An. In other words, this would be the natural log of the product of 1 plus k over n, everything to the power 1 over k. That's beautiful. That's great. So this will be, like I said, this log will transform the product into a sum. And we should be careful here a bit. So this would be the sum of, this would be 1 over k times log of 1 plus k over n. All right, great. But we can write this as 1 over n times the sum from k equals 1 to n of the log of 1 plus k over n, everything over k over n. All right, great. At this point, this is a Riemann sum. This is the Riemann sum for a function, right? And we should be careful how we define this. So this will converge to this integral. Well, here we have a problem with 0, right? So this is like an improper integral. And we should compute it somehow. Well, unfortunately, you can, this is a very special integral. You can try as many techniques as possible. You can try whatever tricks, substitutions, whatever. It turns out that you will end up with, well, it will lead you nowhere. So the only thing you need to come up with is just to use the power series expansion for the natural log of 1 plus x. so which is given by like I said, all right. Now let's use this into our interval. So we have that the integral from 0 to 1 of log of 1 plus x over x dx. So this would give us, let's be careful here. So this would be, let's denote this integral by I. Over n dx. All right. And now we're wondering, well, now our goal is to swap the integral with the series, with the power series, but the question is this series uniformly convergent? Is it? I'll leave it to you. Yes, it is. Well, try to prove it as an exercise. Well, the answer is yes. I'll leave it to you as an exercise, but we have seen the Abel-Dirichlet criterion, or even Leibniz criterion you can use in this case. You don't need to go that far. All right. So if this is uniform convergent, then we can swap the integral with the series. So this would be the sum of time over n times the integral from 0 to 1 of x to the power n minus 1. And this would give us over, this is 1 over n squared. And I'll leave this to you as an exercise to show that this is pi squared over 12, right? Because we use this pi squared over 6. So this is a result of Euler. He made sensation back in the day with this. So we have to use this to prove that this holds true. But anyway, I'll leave it to you as an exercise to do so. We'll go back to this result at some point. We'd like to prove this, and I told you we'll do it, but I just want to do it in a more fancy way, like using differential equations. In fact, I'll use the power series for the arc sine and so on. Anyway, we'll get there. Now, let me share some other applications as well from involving power series, and let's see some application 4. And this was, you will see that there will be a Putnam problem closely related to this problem. So this was a problem which states the following. And actually one of my good friends had it as a preliminary exam, as a problem in his qualifying exam at the University of Wisconsin-Madison. I think it's in 2013. So basically the problem says the following: show that this series is nothing else than just this integral. This is University of Wisconsin-Madison qualifying exam and real analysis. 2013. I remember he told me about this. And in fact, this problem is quite involved. It's a very nice problem. You use all sorts of techniques. You use Weierstrass test, use the power series for an elementary function. I don't want to divulge the function yet. You'll use some integral to computational techniques for integrals, like change of variables, or use substitutions. And then at the end, you will see that this will be related to some properties of the gamma function. Oh, right. So let's do this. Let's carefully do this problem. So first, let's start with the integral. So we'll start from right to left. We'll take the integral and then using some kind of we will write the integral in a certain ways that will make it look more appealing, so that we can use so that we can recognize some kind of a power series for a function. All right, so let's do it. We have this integral. As you know, this by I. So this would be, let's be careful here. I'm going to do the following trick. And this will be the integral from 0 to 1 of e, the negative x log x dx. Wow, that's nice. So I wrote it in this way. It's great, because now we can use the power series for the exponential function, right? So I'm going to write it in this way. So let's say e to the y is this series. So it's y to the power n over n factorial. And we have, let's see. So this will give us that at I, this would be the integral. So let's be careful here. So this would be the series of dx. Okay. So now we have this series inside. If you look at it, and of course, our main goal is to swap this with the integral so that we can integrate. All right, but first we need to make sure that this is uniformly convergent. This series is uniformly convergent. It is, indeed it is. Why is that? Well, we do have the Weierstrass test. I'll leave the details to you. By the Weierstrass test. It's pretty easy to see that it's uniformly convergent, right? But I'll leave the details to you. So, since it's uniformly convergent, no problem. I can swap the integral with the series. So this would give us this. And there we go. We need to take care of this integral right here. We need to take care of this integral from 0 to 1 of negative x log x to the power n. So what should we do? we should be careful here. We should take care of this one here. So let's work this integral separately, and then we'll go back to our series. So let's see. Let's look at this integral. So it's the integral from 0 to 1 of negative x log x, everything to the power n dx. So what should we do about this one? All right. Let's perform a u substitution. So let's just say log of x equals u. That's great. So, or maybe no, maybe negative log of x equals u. So this would mean that x is e to the negative u. Great. So now let's see when x is 0, I'll have that u is negative infinity. And when x is 1, u is 0. So this will be the integral from negative infinity to 0 of u times e to the negative u. And now we should be careful here. So dx is negative e to the negative u du. Dx will be so to the power n times dx will be e to the negative u du. And one negative here. Okay. That's great. So this would be the integral from 0 to infinity of u to the n, e to the negative n u times e to the negative u du. So this would give us the integral from 0 to infinity of u to the power n times e to the negative n plus 1 u du. This is almost looking like the gamma function, right? Almost. So maybe we can perform another change of variable. So this looks almost like Euler's gamma function. I think I've said a few things about it. We should try to work this integral somehow. All right. Let's see. So let's write it again. Pretty computational though, so we should be careful with the computations here. All right, so I'm going to perform the following substitution. M plus 1 u equals v. That's great. So du will be 1 over m plus 1 dv. The bounds will stay the same. So when u is 0, v is 0. When u is infinity, v will be infinity. So this will be the integral from 0 to infinity of so u will be 1 over m plus 1 to the power n times v to the n times e to the power negative v times du, which will be 1 over m plus 1. Ah, that's great. dv. All right, and at this point we're lucky. This looks really nice. So this would be 1 over m plus 1 to the power m plus 1 times v to the n times e to the negative v dv. All right, which will be 1 over m plus 1 to the power m plus 1 times the integral from 0 to infinity of v to the n times e to the negative v dv. All right, and now let's put everything together. So putting everything together, let's see, what do we get? So we started with this series here, right? This one here. We get that our integral I, which was at the beginning 1 over x dx dx, at some point we make it work to look like this one. All right, so it was this series. Times this integral, right? Okay, and at some point, this was, we computed that integral. So this is like, let me write it here. So this was this guy here. So all right, great. But the way we define this is nothing else, and if you look at the previous lecture, this is nothing else than just Euler gamma function evaluated at gamma over n plus 1, which is n factorial. So this is nothing else than just this. And at this point, we're done. So this is nothing else than what we had to prove. Well, like I said, it was pretty involved. It's, the computations were pretty, well, you have to be careful with this problem. I think I would like to do maybe one more problem I have in mind. maybe this is I think I'm going to stop after this one. So this was problem number 4, and one more problem, problem 5. Because this was actually a Putnam problem. So it was a Putnam A3 in 1997. And this problem has all the ingredients we need in the world. So basically, it was just a computational integral. Compute the following integral. It's an improper integral. X minus x cubed over 2, sorry. In fact, what's the statement? I forgot the statement. It's pretty, let me see. So the statement x minus x cubed plus x to the 5th over 2 over 4 minus plus, okay, minus x to the 7th over 2 times 4 times 6 plus so on times the following 1 plus x squared over 2 squared plus x to the 4th over 2 to the 4th times 4 squared. I think it's 2 squared. It shouldn't be 2 to the 4th. Okay. 2 squared here plus x to the 6th. So the next term should be 2 squared, 4 squared, 6 squared, plus so on. Oh my, dx. Oh my. Well, basically, we should recognize some things here. If you look in the first parentheses, it's just, maybe it's the power series expansion of a function, or maybe the product of two functions. So the question is, do we recognize this as somehow? That is the question. You see, it has factorial. So if I remember correctly, the exponential has factorial, right? But it also has alternating sign. So there is no way you can have an exponential of, you have to have some negative sign there. And you see the powers are jumping from 2 to 2. So basically, maybe we should have an x squared. Well, actually, yes, we can recognize. So this expression here is nothing else than just the power series of and we have an x we can factor with x times e to the, let's see, so it's also over 2. Okay. It's negative x squared over 2, I think. Let's see, so e to the negative x squared. Yes, that's it. All right, great. Let's see, do you recognize something in the second parentheses? So let's see the second parentheses. Let's look at it carefully. So this guy here is nothing else than, what is this? So it's the sum see, so I have 2 to the square. So it's x to the 2k, right? Okay, so it's 2 to the 2k times k squared, k factorial squared. All right. So for k equals 0, it verifies, k equals 1. Yeah, that's it. Great. Wow. Beautiful. Then so once I identify these two, I can easily express my integral. So we have that the integral is the following. So this is x times e to the negative x squared over 2 times the sum of this series. Because I don't think I can express this in terms of an elementary, maybe it's elementary functions, the function disguised in some way. Anyway, let's work with it in this way and we'll see afterwards. So this is my integral. So I'd like to deal with this. And in fact, I want to look even better. I want to look inside this. I want to work this thing out inside. So what can we do about this? So this is like a power series. So let's denote this by, say, fk of x. All right, this. Now, let's see. This converges pointwise to what? That will be interesting. To what function? That's it'll be interesting to see. So so this will converge to a function. Okay. All right. So we'll denote this. All right, first before I use because my intention is to use the dominant convergence theorem for improper integrals, right? So let's work this a bit. Okay, all right, so okay, let me be more specific a bit here. So let's consider the following sequence of functions. Fn and Fn of x is given by x e to the negative x squared over 2 times the sum from, I'm going to consider the partial sum All right, so this will converge pointwise. Let's say we take the limit to some function f. Okay, so this will converge to some function. And now let's see if we can dominate this. So moreover, clearly we have this is non-negative. And let's see if we can find an upper bound for this one. So x times e to the negative x squared over 2 will stay the same times. Okay. So now, okay, that's easy. X to the 2k, 2 to the 2k, and here I put k factorial, which this would be e to the x squared over 2. This would be x e to the negative x squared over 4. Just say this is my function g of x, let's say. Well, I'll leave this to you as an exercise, that the integral converges. So now by the dominated convergence theorem for improper integrals, it follows that my integral I, which is the limit that approaches infinity of, okay, the integral from 0 to infinity of fn of x dx is nothing else than just so my fn will be so this is the limit fn. Okay. Oh. K factorial squared times e to the negative x squared over 2 times x to the 2k plus 1 dx. I think that's the, yeah. All right, that's great. So this would be the limit as n approaches infinity of, I think I forgot here the sum. Jesus Christ. Yeah, this is the sum. Oh man, I made a mess of this, but anyway, I think we can make it work. Times the integral from 0 to infinity of e to the negative x squared over 2 x to the 2k plus 1 dx. All right. And again, we can use gamma function, so we need to control this integral. And of course, this is, maybe it's related again to gamma function. And probably it is. We'll see immediately. So we need to control that. So how should we do it? Okay, that's easy. So we can do a u sub So we look at the integral. And we perform this u sub x squared over 2 equals u. All right, so this would be when x is 0, u is 0, when x is, okay, so this would be it. Ouch. So this would be the integral of e to the negative u times. Well, let's see. So this would be two. So it's 2 to the power k, right? And u to the power k. Du. So this would be the 2 to the power k times the integral from, okay, that's the gamma function, which is this guy is gamma of k plus 1. So this would be 2 to the k times gamma of k plus 1, but gamma of k plus 1 is k factorial. All right, let's put this everything together. So this follows finally integral I will be the limit as n approaches infinity of times 2 to the k times k factorial, which is of 1 over 2 to the k times k factorial. And of course, this is nothing else than just the power series of e to the power 1/2, which is square root of e. And that's the value of the integral. All right, yeah, that was pretty involved as well. That was, yeah, with computations and stuff. I hope it makes sense. All right, I think I'm going to stop here. Well, next time we'll in the recitation we'll solve problems from the worksheet number 4. Problems will be very similar to this problems that we solved. In fact, but there will be no theory, only problems. All right, I'll see you next time, and thank you very much. I'll stop here. Bye.